that govern the behavior of matter at these most microscopic scales. And eventually this gave birth to the idea of quantum theory.
The word quantum means a parcel or packet, and quantum theory is a description of nature based on tiny packets of matter and energy. Light can be described in these terms. The packets are called photons, which stream out of any radiant objects, like a light bulb. But there is a problem with light. It can also be described quite persuasively in terms of waves of energy radiating from the source, like ripples on a pond. So what is light made of? Waves or particles? Time for an experiment. The experiment was devised by Albert Michelson, the one who 20 years previously had said that there was nothing left to discover in science. Quite simply, it splits a beam of light, in this case a laser, into two, and sends one beam to the left and the other beam to the right. A little further on, the beams are brought together again, and the result is photographed. According to the wave theory of light, the two beams will create a pattern of bright and dark patches, what are called interference patterns, where the peaks and troughs of the light waves either add up or cancel each other out. In the Michelson experiment, this is exactly what happens, and the camera placed at the end of the laser path does indeed see interference bands of light and dark. But there's a profound philosophical sting in the tail of the Michelson interferometer experiment, as Professor Chris Isham explains.
The basic idea is very simple. You have a light source which you split off into two beams and then recombine so that they interfere. And that's a perfectly normal demonstration, actually, of the wave nature of light. Indeed, it was precisely through that sort of experiment that the notion that light was a wave first came into place. Now, the interesting thing, however, occurs when you turn down the amplitude of the light, make it weaker and weaker. Now, according to classical physics, all that should happen is that the image will get dimmer and dimmer and dimmer. But in fact, what happens, if you look at it carefully, is you'll see it doesn't just get dimmer, it breaks up into dots. And those dots, each one of those dots is in fact the effect of a single photon. So what you begin to see is how this apparent interference pattern is made up of individual photons. In terms of quantum mechanics, one says, well, why that's happening is that what is really going through this equipment is not so much a light wave, which would be the classical view, but a probability wave, if you wish. And what is happening, the probability waves are interfering. Now, this, of course, is a very difficult thing to think about, but it's what the mathematics suggests. And then when the probability waves peak up together, they say there's a high probability you'll get a particle there. And when they, of course, cancel out, they say there's a low probability. And therefore what should happen, according to the theory, is you'll get speckles appearing on the pattern. Lots of speckles where the bright band was, and not very many speckles where the dark was. And in fact, that's what you see. If you look at the screen, you'll see that's what happened. Now, that in itself is not that remarkable until you start asking, how does it come about that each individual photon, as it were, knows what to do? And the only way you can explain this is by saying that in some sense, the photon itself splits, whereas classically the light beam split. You now have to somehow get hold of this idea that the photon is somehow aware of both paths. This is a very, very strange concept.
In quantum theory, one abandons the possibility of predicting the exact result of any given experiment. What one does is one predicts with extremely good accuracy the probability of a certain outcome.